Hey everyone, so we're going to continue our discussion about circular motion, and in particular, we're going to introduce the concept of forces. Now, we already talked about that an object moving in a circular motion is accelerating, and that means that there has to be a net force acting on it. So, we're going to end up calling this net force a centripetal force. Just like the acceleration, the centripetal force also points towards the center of the circle. Once again, that's the whole point of the word centripetal. Centripetal means center seeking. Now, there is one thing that I need to state right now. There is no such thing as the centripetal force. The reason I say this is if you look at the very the last sentence of that paragraph, I explicitly call it a net force. So what ends up happening is that uh, when you draw your FBD, the centripetal force is never going to be added in there. What ends up changing is that one of the forces that is in your FBD, or multiple forces, are going to end up acting as a centripetal force. So, for example, the gravitational force can be a centripetal force in certain cases. Maybe it's the normal force, maybe it's the frictional force, or an applied force, or a tension force, or any of the other forces that we've talked about. We haven't talked about electromagnetism, but that could also be a force acting on it. Whatever force that's acting on it, it's going to um, be what's causing this centripetal motion. So you're going to hear me kind of go back and forth, calling something the centripetal force. But it's important to note that the centripetal force isn't its own unique force. It is a combination of forces that cause the object to move in a circular motion. Now, in this first part, it's only going to be one force, but in later parts, you'll see that it could be a combination of forces. One other thing that I want to point out is that the reason why this is extremely important, at least in the beginning, is because you won't really see too many problems that will say, hey, what's the centripetal force? Instead, they'll be referring to the normal force, or they'll ask about the frictional force. And you'll realize that you don't have enough information to use the typical methods, like setting Fn equal to Fg, or being able to say that the frictional force is mu equals mu Fn. Instead, what you'll find out is that those forces that they're referring to are the forces causing the circular motion. Therefore, what they're trying to ask for is what is that centripetal net force? All right. Now, one important thing to think about is if the forces act inward, why do we end up feeling like we get moved backwards? This is actually an extremely important thing. And one of the main reasons is because of the fact that it's actually not the force that's causing us to go back, but rather our own inertia. Because of Newton's first law, we constantly want to keep moving forward in a straight line, tangent to the circle, which means the faster we spin in this circular motion, the more the wall has to basically force our body to change direction. Remember, the whole idea about inertia is that uh, we are resistant to changing our motion. So, because the moving in a circle requires us to constantly change the direction of our velocity, that means that there has to be a force constantly pushing us uh, inward, or essentially to constantly change the direction of that velocity. And that gives us that feeling of being pushed into the wall. Um, this is actually very similar to the accelerated reference frame questions, like being on an elevator or even being in a car. Like you go in a car and all of a sudden you accelerate. Your body feels like it gets pushed back, but there isn't any force pushing you backwards. Instead, it's actually the car itself, or the seat, that's pushing you forward really harshly, and your body's inertia being resistant to the change in motion, wanting to maintain whatever initial motion you had before. So it's kind of the idea that there's a difference between what we feel and what we're actually experiencing. All right, so for each of these diagrams, I want you to try to figure out what force is the one that's causing the centripetal motion. Which force is acting as a centripetal force? I do want to clarify that I'm just looking for very basic answers. So pause video, work stuff, and we'll go over in a second. All right, so going through this, It's very clear that the wall is what's keeping these people in this circular motion. If I drew an FBD, the normal force would be pointed directly towards the center of their circular motion. So the normal force is the one that's causing the circular motion, that's acting centripetally. Here, what's causing this circular motion is the string. Again, it's a horizontal circle. The only force that actually has a horizontal component is this wire. So the tension force is would be acting as a centripetal force. If I want to be very specific, I would have to say one of the components of the tension. For this one should be fairly easy. The moon is being held by the gravitational force. The gravitational force is keeping the moon in that circular motion. So the gravitational force is the centripetal force. Now the car one's a little bit trickier since it can get a little bit tough, but it turns out that the force keeping the car in the circular motion is the frictional force. Like I said, this one can be hard for people to visualize because of the fact that, unlike with the other scenarios, friction's kind of harder to visualize. Like the normal force is easy to visualize because you can see the wall. Tension's easy to visualize because you can see the rope, and you can kind of imagine it pushing in that certain direction or pulling in a certain direction. Friction's a little bit weirder. Um, but this one makes sense if you think about it. A person driving in a car, making a turn, if they hit a patch of ice in the middle of that turn, they will no longer maintain circular motion. The lack of friction will cause the car to slip and slide, and it will end up sliding out of that circular motion. So again, it's friction what's keeping them in the circle. All right. Now, we have an equation to actually give us the value of this centripetal net force. The first part is Fc equals MAC. Oh my goodness, it looks exactly like the net force equation because, as I mentioned before, centripetal force is a net force. It's just a very special net force, a net force that only comes up in the case of circular motion. What we can do, because this pops up so much, we can actually just immediately combine this equation with our previous equation for AC, which is v squared over r, to get that Fc is also equal to mv squared over r. Now, one thing I want to point out is the way this equation is written, uh, you don't have to write the entire thing. What this basically means is that I can take any two terms and set them equal to each other. So if I want to use Fc equals MAC, I could use this as my equation. If I want to instead use Fc equals mv squared over r, I can use those two. Or I can use MAC equals mv squared over r, which really just ends up being the centripetal acceleration equation. So you wouldn't really use this. But what I'm trying to get at is that this equation, the way it's written, is actually three equations in one. So you'll see what I call linked equations throughout this unit as a way of kind of simplifying and combining everything together. Really quickly, I do also want to make it one more announcement: is that there is no such thing as a centrifugal force. You might hear it in other cases. Realistically, what they're if you ever see the word centrifugal force, it's referring to that idea of a feeling. Again, if you imagine yourself being put into a circular motion, you know that your body is going to get pushed backwards. That's that feeling that you're getting. And in that frame of reference, like let's say being in a gravitron, um, relative to the room, the ride, you are not moving. Therefore, because of Newton's first law, the forces should be balanced. You know, the forces vertically, forces horizontally should all balance. So a lot of people used to believe that there was a centrifugal force that counterbalanced the centripetal force, but that's not the case. Again, the idea is that it's not taking into account the fact that the whole entire frame of reference is actually accelerating and changing. So we actually aren't in equilibrium, even though it may seem like it in a certain reference frame. Um, So I kind of relate it back to elevators, how, when you accelerate upwards in an elevator, you kind of feel like you're being pushed downwards, but that's not actually the case. There is no downward, I mean, besides your force of gravity, there isn't really a downward force. It's just that the ground is kind of accelerating upwards faster than you are. All right. So I just wanted to point that out there, that if you don't use the word centrifugal, because it's not actually a thing, it's the centripetal force that we care about. All right, so I want to kind of go back to this idea about what I mean when I keep saying that the centripetal force is a net force. So, like I said, whenever it comes to forces, you want to approach almost every single one of these problems the exact same way. You first start with an FPD. So let's say I want to know the forces acting on the people on this little swing ride. Well, I know I have a gravitational force going down and I have a tension force going up and to the right. Well, my next step is to alter the FBD to simplify it so that I can use it. So then what I would do is break up that tension into an X and a Y component. Now, because I'm moving in a horizontal circle, I know that the horizontal forces are going to end up being my centripetal force. Now, normally, if I was going to solve this problem, I would have done sum of the forces in the y direction equals 0 to get FTY equals FG. And then I would have said, okay, well, the sum of the forces in the x direction, because they're unbalanced, should be equal to MA. So then I would have done FTX equals MA. The only difference is that because this force in particular is causing a circular motion, instead of using this as just a regular standard acceleration, we're going to pop on a little c and turn this into a centripetal acceleration. So then what I can do is set this ftx equal to mv squared over r. All right. So again, the process doesn't change just because we're talking about this new scenario. We still approach it the same way with the whole FBDs and some of the forces and net force or whatever you want to call it. And any direction where the forces are going to be balanced, where there's equilibrium, we set that equal to 0. If there is an acceleration, like in this case horizontally, we're going to set equal to MAC, and then that's pretty much it. So the only difference is that instead of doing like a change in velocity over time for acceleration, we're doing v squared over r for centripetal acceleration. All right, so I just wanted to mention that. So work on these problems, pause the video, work itself, and we'll go over in a second. All right. So they want us to figure out the maximum speed we can have. Once again, the big thing to take away here is that notice they don't say the word centripetal force. They call this a breaking strength of a string. So very clearly, this is referring to a tension force. So what I can do is set my tension force equal to the centripetal force. So set it equal to MAC, which is equal to MV squared over R. In particular, I really only care about these first two, the first and last part. So plug my numbers in, and then making sure to convert the 80 centimeters into meters. And I get that the maximum speed that this object can have is about 4 meters per second. Any faster, and the string will break. All right. We'll do 2 more problems, and then I'll save the rest for another video. All right, so here's the next question. Pause the video, work itself, and we'll go in a second. All right, so here they want us to calculate the centripetal force. Now this one, it does say centripetal force, but you'll see why in a second. So I just take my standard centripetal force equation. Because I'm dealing with this speed, I'm going to be using this part in particular. So plug my numbers in. They didn't tell us the mass, but they did tell us the weight, which, as you know, we can just divide and get it to be 80 kilograms. So plug these numbers in, and we end up getting that the centripetal force is 400 newtons. Now, the reason I ask strictly for the centripetal force is so I can ask B, which is what force is actually providing the centripetal force? Well, since this is a person that's moving in a circle on the ground, we know that the force that's keep them in that circle, very similar to the car making a turn, is the frictional force. Again, I can think about how none of the other forces make sense. The normal force and gravitational force are acting vertically, so that wouldn't affect a horizontal circle. There's no rope, there's no other person applying a force on him. So the only thing that makes sense is frictional force. It's the only force that would act horizontally in this case. And then the part C is asking what would happen if the radius ends up suddenly decreasing. Now, I want to clarify that I didn't mention in here, but um, the person's supposed to be maintaining the same speed. Now, if you look at the equation, if the mass and the speed stay the same and the radius is suddenly decreased, because of the inverse relationship between the force and the radius, that means that the centripetal force would have to increase. Well, that's all fine and dandy, except the centripetal force is equal to a frictional force. So there is a limit to how much force friction can exert before it doesn't work anymore. As you recall, the equation for a frictional force is F of F is less than or equal to mu Fn, which means that it could be any number below this, max value. If I exceed this max value, then what ends up happening is the static friction that's keeping me in the circle ends up breaking essentially and turning into kinetic friction. So what would happen is that probably should have added that this is the static frictional force, but the force needed to keep me in the circle would exceed my static frictional force, which would end up resulting in the person slipping out of the circle. So that's basically the idea. If you've ever chased someone, you've probably experienced this, that someone makes a very quick turn and they might end up sliding. So that's just the idea. All right, and then this will be the last question. So pause the video, work self, and we'll go over in a second. All right. So the first question says, what is the magnitude of the centripetal acceleration? So just plug it into the equation, AC equals V squared over R. Plug our numbers in, and we end up getting 45 meters per second squared. Part B asks, what's the direction of the centripetal force? So if I look at this, again, centripetal means towards the center. The only point that's towards the center is C. So point C is where the centripetal force is directed. And then part C says, what direction will the plane move? As we've mentioned, the velocity always acts tangent to the circle because of Newton's first law. So I can draw a line starting at this. Since it's going clockwise, it'll go straight to the right, which is going to be towards point B. And that's it. Like I said, you'll see a few more problems using the centripetal force. You probably won't be seeing much of the whole being equal to a net force or being equal to a combination of forces until we get to the third topic of this unit, which is about vertical circular motion. And so until then, we'll do a few more practice questions with this. If you have any other questions, feel free to let me know. Otherwise, good luck and have a great day.